Okay, can you hear me now? Because something was wrong with OBS and now I see that it's being recorded, but I'm not sure that you can hear it. Oh, okay, great. Okay, so without further ado, I probably will repost later the version with cut out the initial technical difficulties. So, let's start. Today's lecture will be an introduction to general idea what we will be talking about in this lecture. This lecture is split into the it has only 9 hours of lectures, so we will end with all of them before Christmas. So few things. First of all, as I said, but not being heard, my name is Jerzy Baranowski. You can find me if you want to in the building C3 in room 214, but the preferred version of contact is either email or Teams. My email is jb@agh.edu.pl. Course materials, including lecture slides, are available on GitHub. There will be a link in the video's description. If you find something wrong in the lectures, you can always create an issue. Slides are being generated in Python, Jupyter notebooks, and are being transformed into this version with a RISE package, which is using Reveal.js in order to automatically create slides from the Jupyter cells. So, as I said, this lecture is a specific kind both for me and probably for you, because it has only 18 hours for the entire subject. In particular, we have the half of it is devoted to lectures and half is to the conversatories. So the lecture, the 9 hours of lectures will consider the main ideas, which will start with general introduction to statistical modeling, so which we are doing today. Then we'll cover entire lecture on the Markov chain Monte Carlo methods of different kinds. Then we move to alternative methods of Bayesian computation, because we'll be working on Bayesian methods. And finally, we will discuss the Bayesian workflow, which is the, let's say, principled methodology of creating models for the plethora of statistical phenomena or physical phenomena that can be modeled statistically, and so we'll discuss how to both validate and construct such models on a higher level of abstractions. However, you will be able to then follow that for your own applications. Regarding the coursework for the conversatories, which will be due after Christmas, we will every person in the course will be assigned a paper on Bayesian methods. I will ask you to send me, please, the a brief, let's say, a brief short paragraph on what are you doing in your PhD. So I will be able to assign you some work that is at least relevant to what you are doing in a way. So and then we will not be preparing some kind of presentations of them. We will be, so let's call it directed reading. Which will be like the person assigned the paper will present what the paper is about, then we will discuss and try to learn as much as we are able to from that paper. So like it will be like a hybrid between presentation and a book club or something like that. So, or a reading club. So you will be able to work on some results. We will do that probably on Teams, unless some kind of miracle regarding COVID will happen and everyone will be available. So it will be less formal, no formal slides needed, just preparation, some notes, we'll discuss, we'll read the paper on the screen and discuss. Of course, everybody should be prepared for reading the paper earlier, but reality is difficult, so we'll see how we'll go later. But I think that would kind of be some more seminar educational part for you, not something to bore you to death, which is typical for PhD studies. Lectures that are not really relevant to your work. So I'll try to assign something that has this Bayesian statistical core, but is some kind of relevant to your work, at least from the stuff you will provide me with your those short descriptions that I've asked earlier, so you can submit me. Generally, topics that we are covering here are partially covered in some resources. So let's start with Bayesian data analysis, third edition by Andrew Gelman. This is a difficult book in a way, with some of the a bit random elements here. Random in not the sense of statistical, but random in why they are here. But it has a big advantages of being free, because this edition was made freely available by the publisher in a PDF, and also there are lectures by Professor Aki Vetari, who is a co-author, that he gives lectures on them in Aalto University. They are freely available on his website, presented using Panopto framework. Other options is Richard McElrath's book Statistical Rethinking, which is not free, but not also too expensive, and also it's freely available. Its lectures of McElrath are freely available on YouTube. The problem with this book, on the other hand, is that this is it was written by someone who is not working as a technical scientist. Like most of work on statistics are not technical scientists, but this one was created by an anthropologist, and some examples there are anthropologically based, and also there is a big focus in the book on the methodology called causal inference. And causal inference is a methodology of creating regression models using graph connections in the models. It has some benefits, but it's also debatable about its validity in more general cases. It can be useful, but need to be used with care, and a really big focus of the book in the book is given on causal inference. So be wary. Different options are case studies by Michael Betancourt, which are available at his website, so also free material. The issue with that is that this will be a book. That was declared by Michael at some on multiple occasions, and so this is still a work in progress. They are being modified constantly. Their cover at the moment more of the advanced ideas in statistical computing and Bayesian analysis. However, at some points it is very it's sometimes too general, sometimes it's too specific, and partially it's hidden by a paywall for the newest results, which are being updated after a few weeks after being presented on Patreon of the author. Different approach that you can read is a book by Lambert, Bayesian Student's Guide to Bayesian Statistics. It is also a good book, but it's an introductory book on statistical methods based. It gives similar ideas as Rethinking. Is less anthropologically biased, and it includes more work on the more examples on YouTube, something like that. There is no settled lectures for that, but it can be interesting read. I am not aware of a freely available version. Also, the format makes it difficult to read from a scan, so be aware of that. Final book I wanted to mention is Bayesian Analysis with Python by Osvaldo Martin. It is a book that is really a tutorial to PyMC3, which is one of the frameworks for Bayesian computation. And this book is more of a tutorial for PyMC3, and the ideas that are giving about Bayesian statistics there are a bit oversimplified, which can lead you to a model that is not really well analyzed before using it. Regarding other sources, you can always look on Twitter. Authors of those books are partially available on Twitter. I'm following personally Professor Vettari, Professor Gelman, Michael Betancourt, Richard McElrath. Also interesting idea is a podcast on Bayesian statistics by Alexandra called Learning Bayesian Statistics. Alexandra is also one of the developers of PyMC3, and there are interesting discussions on all things Bayesian. So what's the point generally? In this course and in my work, I'm focusing on Bayesian data analysis. So how to use Bayesian statistics in order to create models which are grounded in probability. So use probabilistic language to describe certain phenomena. And those models, by this effect, because they have the good principles of probabilistic models, they are very interpretable, because you can understand what part of models comes from where. And moreover, they are maximally transparent, because you exactly know how the components are coming here. So you can both get why such inference was given, what was the reason for such results, and on the other hand, you can understand the structure of the model. So this is an advantage of statistical approach to the approaches used, for example, in machine learning, which is an important part of general data science, where we try to incorporate multiple things in order to get the idea that will be covering our work. So the main approach in statistical models is that while machine learning is similar, they are not really for direct comparison, because such comparisons are generally unfair one way or another. In particular, in statistical models, we incorporate probability. We focus on the interpretability, on how the data is being generated, how data is being considered. We are usually using regression kind of models. We are focusing on uncertainty, and we are not limited to linear cases. However, in machine learning, we usually do not have initial structure or interpretable parameters. We are not focusing on single variables, but we are focusing on the entire data sets. We are not creating model consciously, but the model is being learned directly from the data, and does not rely on structural properties such as additivity or multiplicability. So providing the model with initial formulas on the dependence of parameters or features on the outcomes, but it more creates the result with the with what comes directly from the data. And machine learning has many advantages, especially efficient in a situation of high signal to noise ratio. So situations when we have a lot of good data. Because if we have a lot of good data, everything is easy, and in that case, machine learning has computational advantages, because it does not consider certain aspects of that are present in statistical models. Especially visual and sound recognition or language translations are great examples of successes of machine learning, because in those cases the structure of, for example, of an image, even if it is blurry, we can still get the structure from it. We can see that there's a person or car or something like that. Even there's a bit of blur on the photo. So the noises in the photos or in the images or in sounds are kind of irrelevant regarding the structure. They may introduce some difficulty, but they are not that problematic. And machine learning is kind of black box, fire and forget approach. So you can, let's say, easier start with something, get a model that is working, and then tune it by modifying hyperparameters, which unfortunately are not really interpretable and what they represent. And of course, machine learning works very well with large data sets with multiple number of features, because when you don't have to consider uncertainty, the advantages of computation in machine learning might be very substantial. However, on the other hand, statistical models is good for smaller data sets or less representative data sets. It can provide you with uncertainty estimates of how your predictions or your classification works. They give you transparency, so you don't have the problem of not knowing what's inside your model, and you can investigate the influences of individual predictors on the entire model in a way. And really, statistical model is the only way to obtain interpretability. The so-called explainable AI is a myth. You cannot really explain what the neural network is doing, especially more complicated one. Only way to create a model that will be understandable and you can interpret its results is only through creating it from the base up with knowing exactly what's going on. In many cases, machine learning might need more data for the same problem as statistical modeling, because statistical modeling can, especially in Bayesian framework, can incorporate the prior knowledge, expert knowledge into the model in a way that will influence the predictions. In statistical models, you need to specify the interactions between variables. However, in machine learning, you can determine them more freely. Machine learning can result in very good classifiers and predictors, but uncertainty is not handled that well. So in case of problems with uncertainty, there are some problems with machine learning. Machine learning, because of it is on the entry level much easier, has many vocal advocates that will promote machine learning as a solution to multiple problems, and which is not present for statistical modeling because it requires more work, generally, especially conceptual work, in order to get the model working. And finally, statistical models requires data reduction for larger data sets, because in the case of multiple too large data sets, you get problems with fitting of models. So when you can use statistical models, when the uncertainty is important, so you not only get a prediction, but also how risky is the risky will be that prediction. What kind of can you predict, for example, what is the expected gain or loss based on your prediction if you are on the error side? You do not have perfect training data. You want to isolate particle variable effects. Sometimes you have structural information, you have smaller samples, and interpretability is important for you. On the other hand, machine learning is for situations with low randomness, high signal-to-noise ratio, lot of data. General result is the prediction, and uncertainty is not that important. Non-linearity and unknown expected. You have huge samples, and you can accept lack of interpretability. In case of Bayesian statistical modeling, we have really creation of three essential steps. We need to set up the full probability model, we need to condition that model on the observed data, and check and evaluate this model and its posterior distribution. And you can repeat that if necessary. Those steps allow you to create a statistical model that will be able to analyze the individual steps, to analyze the phenomena that we are interested in. In case of, when we are talking about Bayesian paradigm, we are not talking about classical statistics, because there are main differences in case of Bayesian statistics and frequency. First of all, in case of frequency statistics, you expect that the parameter of interest is fixed. This is some kind of value, and you try to infer how, especially about uncertainty of your prediction, on how the data would change, how would your prediction would change. In case of Bayesian statistics, you know that your data is the only data that you have, so data is fixed. However, parameters, on the other hand, are uncertain because we have limited information about those parameters. So we do not have certainty of what the parameter value will be. We only have some kind of probability distribution of it, because generally in Bayesian framework everything has a probability distribution. Moreover, the difference between in the Bayesian framework from the classical framework is that you include something called prior knowledge. So you introduce what do you know about the process into the inference problem. What does it mean? It means that, for example, if you know that your variables are highly unlikely, let's say temperatures, are highly unlikely to go outside the level of the, let's say, room temperature. So it's very unlikely that you go much below zero or high above, let's say, 60 degrees centigrade. Then you can assign the probability that will put them very little probability to more extreme values, and because of that your model will be already constrained in its parameter space to areas that are reliable. So when, for example, you get a result that is inconsistent with your prior knowledge, then it's a signal to maybe not consider that, for example, because it represents the sensor error, because this is something that you included into your work. What's important? Bayesian methods generally work, and that's their main advantage over the classical statistical methods, because Bayesian methods were, let's say, ridiculed, at least very actively discouraged for multiple years since their development by actually not Thomas Bayes but by Laplace, who discovered the results of Bayes and created the entire modern methodology for mathematical computation in this aspect. However, over multiple years, while statisticians disliked Bayesian methods because of multiple things. First of all, that prior knowledge is not fully objective. You can consider certain subjectivity in creating prior knowledge. That discussion of what should be a random variable and what shouldn't be a variable. And moreover, computational difficulties arising in considering the Bayesian statistics, which we will cover in a moment. The ideas of frequency statistics, which allow quick analytical computation, were much more represented in science, and Bayesian methods were discouraged. However, over years, many methods, many cases shown that the Bayesian theory showed that it just works in real situations, which cannot be said over classical frequentist methods. It was popularized in the insurance businesses. It was got great successes during the Second World War. And there's a great book by Sharon Birch McGrain, which is a popular science book about how the Bayesian theory, while it being discouraged, still started to get to the over 2 centuries of controversy, managed to get into the wide use today. So, book is interesting. It's, for example, available for free on Audible if someone wants to hear it. It's a very good book. Anyway, Bayesian statistics are mostly used in situations where we do not have the comfort of strong mathematical models. So social sciences, medicine and biology, public health, those are areas where you do not have mathematical models coming from physics or somewhere else that you could efficiently use for your computation purposes. And similar situation when you want to model uncertainty in experimental sciences, in physics, for example, somewhere when you need to get not only the actual values but also uncertainties. It is useful for diagnostic systems when you want to get the probabilities of failure or probable expected time, and of course decision support systems when you can easily get the predictions of potential losses coming from wrong predictions. or estimated fairness. So in Bayesian data analytics, we have certain concepts that we'll be referring for our course. We have the observable parameters, which are values that we can measure, and unobservable that we are usually interested. We have parameters of the model that we usually want some kind of inference. We have the data, and of course we have some kind of predictions. We have observational units, which we observe, and we have variables of our models. We are interested especially in a situation of exchangeability, so situations where which makes our life much easier. Exchangeability is something similar to independence, but is a bit weaker. Generally, we can say that, for example, when you are covering the exchangeability is a situation when you can change the order of your results in order to, and it would not influence the model behavior or the phenomena observation by itself. For example, when you are tossing coins, you are not really interested in the order of heads and tails are coming. You are more interested in the general numbers of them. So those are exchangeable with each other. So you can switch those models. We can have also a situation of conditional exchangeability. That, for example, when we are surveying people, people are not exchangeable with each other. For example, they are from both genders, and their gender influences has some kind of relationship to their answers. So you cannot switch their answer anyway. However, if you are conditioning on the gender, so you can treat a data sample of answer and gender together, then those will be exchangeable in the entire set. Of course, our models have some explanatory variables, which are usually used in order to get some predictions on analyze the observed data. Very important aspect is the hierarchical modeling, where you want to, in many cases, you assign probabilities not only to the parameters, but also those probabilities assigned to a parameters have their own parameters, and this can be hierarchically realized situations. For example, it can be a situation that, let's say, you want to estimate is considered, for example, multiple groups in a process. Let's say that you want to estimate the taste preference of a group, and the group considers both male and female, and you know that they have different tastes. However, you can assume that there is some similarity in their tastes because of generally they being still human, so their behavior should have some kind of similarity. So, for example, you know that their preference for certain tastes is governed by certain distribution for each member of the group. However, all those tastes come from all those individual preferences are distributed according to certain other distributions. So you have a distribution of distributions. The hierarchical modeling is a great advantage of Bayesian statistics, and also it's computational difficulty because it's getting difficult to fit those models. And final concept that is important are utility distributions. So situation when you have some kind of utility function that is dependent on your model parameters or your model predictions. For example, a monetary gain of your process depending on the value on the inferred values. So utility distribution is that you can model the distribution of this potential profit depending on the uncertainty of your model parameters. So you can create simulations that will allow you to reconstruct such distribution. And finally, what is important, and you should keep that in mind, Using Bayes' theorem is not based by itself. Bayes' theorem can be used in multiple areas of mathematics and classical statistics also. However, quantifying uncertainty with probability is a Bayesian way of working. Let's start with that Bayes rule, which of course comes from the classical result of this is one of the simplest results to obtain. That comes from joint probability, and using relatively basic transformation, we can see that probability of theta conditional on y is equal to the fraction of probability of theta by itself and multiplied by probability of y conditional on theta. So, and this is all divided by a total probability of y. So generally sum over all possible variants of theta of pairs of probability of theta times probability of y conditional on theta. Probability of theta is called prior information or prior distribution, which gives us prior information about how theta is behaving. On the other hand, probability of y conditional on theta is so-called likelihood. It represents how well our model for given theta corresponds to our data. And knowing that this fraction, we can get the probability of theta considering the information that we have. In most applications, we focus only on the numerator because in many cases probability of y is just a scaling factor. And for example, if we are looking to either to find the maximum of the distribution or to quantify its behavior by samples, we only need the multiplication of prior distribution and the likelihood, which will give us the posterior, which is proportional to those things. It's not equal, but it's proportional. So there is a constant independent on theta that is the proportionality constant between them. And generally, our predictive models allow us to do predictions, and there are two important kinds of predictions. First of all, so-called prior predictive distribution, so gives us the predictions of what can we expect before actual measurements occur. So just using our prior knowledge. And formally, this is a probability of y obtained by integrating out theta out of the product of prior and likelihood. So considering them as functions of theta, we integrate that. Of course, in practical application, we cannot do such integration because general integral calculus is not possible analytically in most cases. So what we have here is the idea. We will discuss how to create it using simulations later during the course. The second variant is so-called posterior predictive distributions. So what values of new data can we obtain, can we expect based on previous measurements and prior knowledge? So this is done in a very similar way. We just integrate theta, but out of the product of our posterior probability, so the probability of theta given y, multiplied by a new likelihood functions, which is just a model of y, allowing us something y, knowing the theta. Finally, additional notions. Of course, everything is conditional. So whenever we consider any kind of distribution, we need to be aware that some kind of there are hypotheses that are supporting our assignment of probabilities. It is never everything just like that. There is always something happening. For example, when you are tossing a coin, you assuming that it's a random event. This is the assumption happening here. If you start to consider the skill of person flipping, their finger strength, something like that, then completely different models happen. And of course, important things are expectations, which are the integral over u of probability density function multiplied by traditionally the value, but it can be any kind of function of u. And of course, variance, which is the expectation of the function, which is the square of difference between expectation and the value. Important aspects also changing variables depending on the continuous or discrete distributions. It is either multiplied by Jacobian or not. We will not be discussing it too much. We use variable changes very often in statistical computation because it makes our lives much easier. Usually it happens when we consider the spaces where the parameters are constrained. For example, with only positive values of measurements, positive value of parameters, or constrained to an interval. So it is much easier to get an unbounded model, for example, linear model, and transformed its space to a constraint, let's say, positive or constrained functions. And we use logarithmic or logit transformation or probit transformations for that. We try to discuss the general ideas of creating Bayesian model with a simple model, which is the simplest possible model, which is the one parameter model, which still is useful because of being building block for more complicated models, and it answers such questions like the average difference between the groups, or strength of association, or dependence on certain variable, or variation between groups. So generally very simple model, but we will make, considering only one parameter model, it will be much simpler to get the general idea. And one of the easiest model with single parameter models is the binomial model, which is a model that represents the sequence of n exchangeable trials. So events that are unrelated to each other, however, we want to with given probability. We have two possible outcomes, which are conventionally labeled as success and failure, and of course the distribution is given by the scaling factor times theta up to the number of successes, and 1 minus theta up to the power of complementary number of failures. So total experiments minus all the successes. And as an example, we'll go to the video games ideas. So let's consider the Mass Effect game. So probably some of, if you have already played in your life, one of the aspects of Mass Effect that you can see is the idea where you are scanning planets for resources, and the scanning of planet for resources is considered that you are dropping the scanner on a planet and get what kind of values are in that given point. In case of what we are doing here, we will not be launching probes, but we will consider the idea of finding water on the planet. So only one simple resource, and we consider that the true proportion of water covering the entire planet is P, so like P% of the planet is covered by water. So a single probe of the globe has the probability of P producing water, so W, and it has a probability of 1 minus P of producing land. So we are just dropping the probe blindly on our planet and we get the information. And of course each probe is independent of each other because we are just shooting those probes without much consideration. And let us consider a situation when we have the, I think I've skipped one slide too much. We can consider a situation when we will be doing the such sampling just by assigning number of successes. So for example, assuming that we have 7 successes and in 11 trials, we can assign, of course, using our likelihood model, we can just get the values of theta corresponding to our variables. So after such substitution, we see that this model, considering of 7 successes in 11 trials, gives us the probability that theta is rather larger than 0 and smaller than 1, locally it's somewhere here, it's certainly not 1/2. How does it work analytically? Generally, the posterior distribution, assuming that we do not know anything about theta, becomes beta distribution. And beta distribution is just a function of theta, because y and n are now fixed. We have 11 trials, we have 7 successes, so this is just a function, a power function of theta, and beta distribution is generally represented in a form of parameters y plus 1 and minus 1, y plus 1. This is the form of beta distribution. And having that posterior distribution, we are really interested of how such inference happens. So how to get the information about theta knowing the probability distribution. And the perfect version of analyzing the model is by its own probability distribution. Probability distribution is the best model because it concentrates on the information. However, analysis of the entire probability distribution, especially in the cases of more than one dimension, is really not possible. So we try to quantify some way in our quantity of interest, so value, numerical value that will represent our distribution, for example by mean, median, or mode, generally some kind of expectation of a function of considered variable, and the uncertainty about it, so either standard deviation or interquantile range or some other quantiles, so it will give us the information about the uncertainty. In multiple variable case, we will be covariance matrix, for example. Or we can use, for example, interval summaries, which will just say us what the interval where the most probability is. And for example, it can be a central interval that is just a symmetric interval around, for example, mean. This is a known result of mean plus minus 1 standard deviations, which in normal case gives us 67% of probability. And the other version is highest posterior density region, so the smallest interval containing desired probability. For a symmetric distribution, they are the same. For an asymmetric distribution, they can differ a lot. In most extreme cases, in case of, for example, two-model distribution, symmetric interval around the mean will be continuous, and the highest posterior density region will be disjoint because it will just focus on those two RVS to get the max probability in the smallest possible interval. And let's talk about priors, because in our first example we just considered no prior information. We just decided that the prior distribution we knew nothing about water, so we generally provide uniform probability distribution of theta, which is just a 1 in our case. Priors generally you can interpret in two ways. One way is so-called population interpretation. So it's the prior distribution represents a population of possible parameters values from which the theta of current interest has been drawn. So it comes on representation of previous population or our state of knowledge. So we express our knowledge and uncertainty about theta as its value can be thought as a random realization from the prior distribution. Generally, both give the same results. This is more a conceptual idea to discuss. And we can consider three main kinds of priors. Uninformative priors, which do not introduce any information. Informative priors that try to introduce new information. They can be often interpreted as a knowledge from previous experiments. For example, in binomial example, we can use a previous experiment with considering theta distribution for beta distribution, which will be dependent on two parameters and is equivalent to having previously alpha minus 1 prior successes and beta minus 1 prior failures. So informative prior introduces new information. For example, what we knew about ranges of parameters, We generally want to use informative priors if we have information. Worst case is that we do not have information, but we give some blind assumptions and we inform our posterior distribution by ourselves without much justification. That's why the non-informative priors were popular, so because people were afraid that they are just adding too much and just wanted to get Bayesian theory to support the classical frequentist results. In our case of binary distribution, using informative prior of using from beta distribution, we get a very nice closed form of final result, because multiplying our likelihood and our prior information, we get a posterior in the form of a beta distributions with new parameters alpha plus y and beta plus n minus y. So the alpha and beta come from the previous experiments, y and n come from the new experiments, and what is important, that we, knowing beta distribution, we can get the expectation of distribution analytically, because that's the merit of using known distribution. It has computed certain values available. So we can see that our distribution is the quotient of alpha plus y divided by alpha plus beta plus n. And what is important is that this value represents us the most important aspect of what is prior and posterior difference, because this expectation always lies between just the data, the sample proportion, number of successes divided by number of results, because if those two are equals to 0, that's just our results. And when beta beta from 0 with parameters alpha and beta equal to 0 is just a uniform distribution. So in case if we had no prior knowledge about successes or failures, then our result is the just the average of average number of successes. In case we have no information about new experiment hasn't yet started, n is equal to 0, so of course y is equal to 0, our model reduces to the mean of the prior. So what we know about theta is only what we knew about prior, and this very simple example gives us the main scope of the Bayesian methods, that we are creating a compromise between prior information and new information in order to create the information of the distribution of possible values of parameter of interests, in case of theta, of our model. In that case, to be able to create the values of so that such compromise depends on how we construct our model or what kind of likelihoods we've used, because there are multiple aspects that need to be considered. But the generally this simplest example gives us the result that happens in all the cases. How to weigh between new data and old knowledge to get the appropriate result. This is a special case, actually, which is called conjugacy, which is not that very important, but it's just I wanted to mention it, that certain priors are so-called conjugate priors, and they are very useful to get analytical results. But in practice, they are very rarely used, so we won't be discussing them too much. Let's just get an example of computation with more like real data, and this is a biological aspect called placenta previa, which is the very specific way of birth where the placenta moves before the baby during the birth. And there is a question: is the proportion of girls born with placenta previa lower than the proportion of general number of female births in the population? So is this less common than number of years? So we had a study results with 980 births, 437 were female, which is normal probability of female birth is 0.485. And we can do it computationally because we can assign this information. We can assign the uniform prior. The analytic computation gives us the posterior of beta equals to beta 438 times 544, and we can compute it directly using samples. So we want to get the highest density interval, so 94% density interval, and so we want to get a median from that. So from just the distribution obtained in the example, so from these 980 cases, we get the information without any prior knowledge. We get the interval that probability of female birth in such case is between 41 and 47%, with a median value of 44%, which we can visualize here. So this is our beta distribution, and this is the interval that that contains 94% probability. And because for binomial likelihood beta is conjugate, we can of course encode our knowledge regarding the population using the following relationships. First of all, we were given the mean of the entire population of female births, so we can, using that, compute alpha and beta, considering that beta is previous experiments, so alpha and beta is the population size. So we can use our prior in a way that it represents certain previous population with the same mean as the entire population. So having the mean of 0.485, we have we have accumulated a lot of data. But we'll be varying how large previous population will influence our inference on the births. So we consider populations of 2 people, 5 people, 10 people, 20 people, 100, 200, and 1000, and we'll just compute highest posterior density intervals in all those cases. And depending on size of population, we can see that the posterior median is slowly rising towards consider the example, assuming that we expect that the population, assuming that our prior, we want to consider a situation when is our new data providing evidence for the less frequent female births than in case of normal population. Assuming that a normal probability of female birth is 0.485 in a population of 1000, so that's an expected value of birth up to 1000. We can see that increasing the number of populations, number of samples, we see that prior knowledge dominates, that our data is still not inconsistent with the prior knowledge before. As you remember, here our original interval is between 41% and 47%. Introducing the prior knowledge suggests that still especially lower probability is subsequently rising. That the probability of getting the female birth is the lower end of confidence interval is moving upwards. The same like the upper end. So we are moving towards the original mean because a lot of data, previous data, supports that hypothesis. And we can see how it happens here. assuming the prior population size is depending on the prior population size, we can see that if prior introduces little information, posterior and likelihood are identical, and so this is the posterior with uniform prior. And if prior introduces new information, more and more information, with 100 people it is still not very reliable. With 1000 people is much more. So it moves our posterior probability towards the prior. So large information from the prior moves us towards away from just the sample towards the earlier expectations. If we did not have, if we, on the other side we introduce this new data, a lot of new data, we would move to the other side. This is, however, a very useful situation where we have little data points about certain cases, and we want to get, and we can have only prior to rely on them where the data came from. So let's move to the general cases. So we want to move to the expectations, because this was a very simple case when we have an analytical computation, but this is not something that really happens. So we, in general probabilistic computation, when we want to get some kind of information for our data, we want to compute an expectation of certain function of the parameters. And so parameters are given by their distribution, and we want to compute an expectation of the certain functions. Usually it might be mean of those, but just the mean of the parameter, but sometimes it might be more complicated. This can cover all kinds of the statistics. Assigning appropriate function to every expectation will be computed, we can get a lot of different results, and this code has many beneficial properties. Especially that such expectation is of course given by integrating over the parameter space. Using the probability distribution of parameters, we get the of our function of those parameters, and these can be computed analytically through integrals, or in discrete case just by sum. And generally, computation of expectation might be difficult, because without reducing ourselves just to easiest cases, the analytic integration is not something that happens. Analytical computation of integrals is not something that is really possible in practical applications. So we are usually left with quadratures, so numerical integration. One of the easiest ways, of course, is the Euler quadrature, when we divide our space of possible values of Q into some subintervals, and we just sum over those subintervals as discrete values, for example, at the beginning of the interval. And that's one way. Different way that is popular in statistics is generally computing some called Monte Carlo estimators. So if we can estimate set of samples from our distribution, and we have such situation that increasing the number of samples, our Monte Carlo estimator of the expectation, so the average of those samples converges to the actual expectation, then we have an exact sampling procedure. So exact sampling procedure is the best thing ever, because we have a distribution, we can get samples from the distribution according to the distribution, and it will give us our expectation at this infinity. If samples are generated properly, then we can quantify the estimation error using the central limit theorem. Why? because this sequence, or like this sum, is an average of random variables. Those are random variables potentially independently distributed because each of them is sampled independently from distribution. So the sum of independently distributed random variables has a normal distribution with an expectation equal to the mean value and the variance given by standard variance of the sample. And this is a central limit theorem. And if our sampling procedure converges, then we have a situation that our samples are being distributed as a normal distribution with so-called Monte Carlo standard error, which is equal to square root of our sample variance divided by n. So let's create it in most simple way. We create a grid approximation. A grid approximation of our posterior distribution. So we divide our posterior distribution into the sequence of points, and in each of those points we will be computing values. So we compute the value of prior at each parameter value of the grid. We compute the value of likelihood at each parameter of the grid, and multiply the prior by the likelihood in each point. So we have the numerator of the Bayesian theorem. Or in other words, numerator of the probability distribution approximated by approximation of the numerator of the distribution. And as we remember, the numerator from the actual posterior distribution depends only by proportionality. This proportionality is the thing that will guarantee that the entire probability distribution integrates to 1. And for that we just divide each value of for each of the points of the grid by the sum of all the values. So we approximate the total probability of y by a sum, and in this way we create the approximate probability distribution. So this posterior grid approximation looks like this for given number of points, assuming number of successes. Let's go back to the globe example. Again, we define our grid, which contains uniformly distributed points on the 0-1 interval. We define the prior, in this case a uniform prior. We compute the likelihood. We multiply with some. That's it. Which can we of course plot as obviously increasing number of points in the grid increases the quality of representation of our probability distribution. So what can we do from that? Having this approximated prior, we want to simulate data from posterior. We want to simulate data from that posterior, because the easiest way to compute those expectations would be using Monte Carlo estimators, so just getting the appropriate samples. For single parameter problems, the easiest way is to use the inverse cumulative distribution functions from the formula, but that will require us to know the formula, and grid approximation is generally universal because just we have the values from the probability distribution function. And we can, depending on number of successes, we can just create with multiple priors, we can just get our posterior approximation, which generally changes just by changing a prior. For example, we have a uniform prior, we have truncated prior, so only values greater than 1/2 are possible, or we have the double exponential prior, which is more complicated. Okay. So, for example, in this case here, we have depending on what kind of grid we want to use, we can use the prior or posterior grid. Our function can be used to computation both of priors and posteriors, because we can just provide zero information about successes and failures, and we just stay at the prior. Depending on what we want to use, if we want to use uniform prior, it will look like this. If we want to use the truncated prior, it will look like this. And if we want to use the double exponential prior, it will look like this. So generally not complicated situation. Probability of depending on the having the same data, depending on the prior, we get different locations of our parameters, but it's still that this distribution is relatively easy to compute, and we can sample from it. Okay. Sampling from a distribution, we can of course get a histogram of those samples, and this histogram will look generally as a probability distribution function up to a scaling factor, because here we have we don't have it normalized. From that we can of course compute all kinds of statistics, so our expectations without considering here standard errors. We can, for example, estimate the probability when p is less than 1/2, which we can do using the generally expectation of the appropriate indicator function here, which we can do generally in two ways, either by computing directly from the posterior or by sampling from the samples. From the samples, of course, is much easier than in this case. The same way we can compute the intervals of interest or quantiles we want to. The same model can be used, of course, for prior predictive distribution, because sampling from our distribution gives us, it is relatively simple, just using the prior probability distribution, we can get the samples from the using the we can sample samples of p from prior and then use it as in a binomial distribution to get the probability of each sample, and we can then estimate then, based on our prior knowledge, the mean rate of success will be 1/2, which we can then visualize here. That is generally sampling from prior gives us the relatively half and half. Posterior predictive distribution uses the knowledge that we already get from the data and works the same way. We just sample values of p from the posterior, and then we can use it to, in a binomial distribution to just get the mean rate of success, which we can see is 58%, which again represents in bigger histogram of samples. But the problem is that this was very simple, and unfortunately life is not that simple, because grid approximations would be very nice, it would generalize well, and in certain aspects grid approximations are very good. In partial differential equations in 3 dimensions we can do something with grid approximations, like finite difference methods or something like that, especially. But in case of probability, the problem is that our probability density function has this property that it has to integrate to 1. So it might be difficult to sample from the distribution in multiple dimensions, because at least approximate it efficiently, because if function has to integrate to 1, then there has to be a lot of space when it will be 0, and depending on the geometry of the function, we might find a situation that our grid points are not very well corresponding to important values of our functions, because they just are located in spaces where it is 0. And it all comes from the fact that is an integral, and this integral, usually we are focusing on the integrating functions. So f is function that we want to compute of q, and pi is the probability distribution of q. And our intuition from, which we should have from the differential calculus from our studies, is that generally for the integral we should concentrate the most around the maximum. Because where the maximum of q is, then the most integral is. So the more and more information we have here, the better situation. Like, we can ignore the situation where pi of q is little, because the most important fact is when pi q is large. And this is true if q is one-dimensional or low dimension. However, if we go to higher dimensions, then this element dq that we usually ignore, this here, is not really negligible, because as we can see, when we divide, for example, an interval in one axis into 3 parts, then 1/3 is here and we lose only 2/3. If we try to do the same thing in 2 dimensions, situation becomes more complicated, because one interval we want to replace with a cube or with a square, but this square from this interval of dimension of 1 drops not only on things on the side, but also on the top and in the corners. So while here we have 1/3 of the interval, here now we have only 1/9. So if our maximum was here, then the maximum was dominating, and most of the area here was okay. However, when we increase the dimension, then this point is much smaller, and integrals over small areas have relatively little values. And if we go even more dimensions, in 3 dimensions, so we can see that the cube in the middle is only 1/27 of the entire area. So increasing the area, the number of dimensions, causes us the fact that location in small areas constrains us to very small volumes. So as we can see, as when we move away from the maximum of q, which is located in a point, the probability distribution function here is larger, but the volume around the maximum is relatively small. The further away we move from the maximum, the more and more volumes is here. So we have a situation that exponentially growing volume is multiplied by a non-zero part of the distribution, which can then rise much higher and contribute much more to the integral, because as you can see, volume here was so small that the maximum of the distribution was located here. And the product of the probability distribution and the volume is something like that. So it's the most of the probability is located somewhere away the most of the expectation integral is located somewhere away from the mode. This of course is in the multiple dimensions, so we have the distance of this expressed as the distance from the mode. And what does it mean in our case? In our case it means that in case of analytical integration it doesn't matter anyway. But analytical integration, as we mentioned before, doesn't happen. But when we want to generate samples to represent our integrals, or we want to create grids, those grids should be here, cover this area, and this area is unknown a priori, because if we knew it, then we had everything about this. But in multiple dimensions, this area where most of the volume is very difficult to find, especially by a deterministic procedure. This part is called the typical set, and it contributes the most to the expectation, so the most important factor. So if we knew the complete geometry of the typical set from the equations, then the problem of computing expectation will be trivial, but we don't. This is a very complicated differential geometry problem that is not solvable. However, there is a way to go there by some kind of sampling. And typically, the typical set is kind of a surface, a fuzzy surface that is located somewhere away from the mode depending on the increasing of the dimension. So here is the most important aspect of here. We should, if we take samples from the typical set, then those samples would be good approximation using Monte Carlo estimators of our expected values. And depending on multiple approaches, we have the multiple computational algorithms that can be used for probabilistic computing. Classical point estimators just use the maximal value. Point estimators that just find some kind of values. Laplace estimators, variational estimators, Monte Carlo estimators, Markov chain Monte Carlo methods, those are different typical algorithms. Generally, point estimates considered, for example, finding the maximal value to obtain approximation of the expected value. It can work well if the distribution is relatively well behaved, but if the distribution is skewed, then the maximum is far away from the expectation, and if the set is relatively symmetrical, then the uncertainty is easy. If the set is difficult, then the problem is bigger. Laplace estimators, on the other hand, is an idea that we want to find the maximal value and find the Gaussian distribution with a mean and covariance obtained by the Taylor expansion of the procedural distributions. And then we can just use Gaussian integrals to compute expectational intervals. And if the distribution is not that different from Gaussian, then of course typical set will be well approximated, because so the samples or the values will be well computed. However, this problem might be difficult in other cases. Variational approximation is the idea to approximate the entire posterior with some kind of sum of functions that can be easily sampled. It's an idea similar to the approximation theory. So we want to create the approximation in some kind of way that of useful functions. We could use approximation by splines in classical function cases. In here we want to use, for example, multivariate normals or something like that. And it is done by minimizing special function called the Kullback-Leibler divergence, and it can measure how two distributions difference each other. And the problem with that is this approximation can be multimodal, so we can find multiple candidates with similar divergences that are differing a lot, and that may have a lot of problems in applications, and also problems with testability. Moreover, we can get a result of over or under fitting the typical set by these approximations. Monte Carlo sampling, of course, is very nice, because this is sample from distribution, but unfortunately not that very possible. because generating samples from a given distribution is a naturally very hard problem. If you know the distribution, it's low dimensional or normal, it's simple. If the distribution is complicated, there's a problem, and there are some kind of methods, like for example importance sampling, that you sample something from its node you know, and you correct that, and it's difficult sometimes to work properly. Markov chain Monte Carlo is, let's say, a state-of-the-art of current methods, which is based on the idea that we construct the sequence that should find and travel around the typical set. And that we will discuss on the next lecture. We will focus on the Markov chain Monte Carlo, which is generally the state-of-the-art at the moment, of multiple problems of reasonable sizes. And we'll discuss how it works, and we'll have a detailed discussion on Markov chain Monte Carlo methods. And on the third lecture, we'll cover the rest. So we'll cover the approximations, variational approximations. We can say approximate Bayesian computation and some other stuff that is popular, and we'll discuss what are the problems with that. And then we'll finally move to the Bayesian workflow, so how to use those methods to solve the solutions. Are there any questions for now? I assume 10 seconds of delay, so ask if you want to. If you don't have any questions now, you can of course ask them on email or on comments to the video, and we will be able to discuss it in the or in next lecture, or answer in the comments. So any questions? Those lectures will be available on GitHub. The link will be under the video. So when I'll make a push, you will get all those slides from today. Any other questions? If no questions, then thank you very much for participating, and see you next week at the same time. So good night.